Hello, I'm Pierpaolo Mori, a PhD candidate at Politecnico di Torino University in Italy, and today I'm happy to present the shared work with the title Wino Vidi Vici, Conquering Numerical Instability of 8-bit Winograd Convolution for Accurate Inference Acceleration on Edge. First, let's start with the motivation of our work. Nowadays, convolutional neural networks have shown to be effective on many computer vision tasks, such as image classification, semantic segmentation, or object detection. However, the deployment of such model on resource-constrained hardware remains challenging. Therefore, CNN optimization techniques are needed to mitigate these challenges. On one side, quantization can be adapted to reduce the model footprint by reducing the bitwidth of the network parameters such as weights and activations. This enables low-precision arithmetic on the edge that results in a faster inference, but only if the hardware can take advantage of lower bit representation. On the other side, convolutional operation can be replaced with faster algorithms, such as FFT or Winograd convolution. These algorithms are able to reduce the number of MEC operations needed to perform the convolution operation. In our work, we focused on the Winograd-based convolution, Winograd algorithm, that mainly consists in 3 steps. First, inputs and weights are transformed using the transformation matrices B and G from the special domain to the Winograd domain. Second, the element-wise matrix multiplication is performed on the transformed matrices. Last, the special output feature maps are produced by applying the inverse transformation. This results in a transformation of the convolution operation in a simpler and faster element-wise matrix multiplication. However, when Winograd algorithm is linked with quantization, it starts to exhibit a numerical instability that causes a severe accuracy degradation. As an example, ResNet-18 model on CIFAR10 on 16-bit quantization shows a degradation of 72% when Winograd 4,3 algorithm is used. We therefore analyze the sources of the numerical instability. First, the numerical range is enlarged when the spatial tile is transformed to the Winograd domain. Here, it's important to notice that although the range gets larger, most of the values are still contained in a much smaller range. Second, the rounding error that is intrinsic of the quantization operation is exacerbated by underutilizing the quantized range. In this work, we tackle the challenges of 8-bit quantized Winograd convolution by introducing Winograd-based convolution using complex number system at training time, by introducing a trainable clipping factor for quantizing transformed parameters in the Winograd domain. Last, we combine training with complex numerical representation with trainable clipping factor in order to conquer quantized Winograd instability. We break down the proposed methodology into quantization-aware training, Winograd-aware quantized training, clipping factors in the quantized Winograd domain, and complex number-based Winograd algorithms. Quantization-aware training is a standard approach for training networks with constrained bitwidths. To achieve this, we require some discrete functions shown on the slide. These discrete operations block the gradient flow during the training. For this, the standard approach is to rely on the straight-through estimator to approximate gradient information over discrete functions. Inspired by quantization-aware training, we moved to Winograd-aware quantized training, where we model the overflows during the training. The Winograd algorithm can be combined with quantization during training. Here we extend the use of the straight-through estimator to apply to the quantized steps of the Winograd convolution. All in all, by modeling the Winograd transformation as well as quantization in the training, we are able to compensate for the numerical instability problem. Building on top of the Winograd-aware quantized training, we further reduce the numerical instability by also making the quantization itself choose its clipping factor to minimize the overflow, which we captured in the Winograd-aware quantization training step. Recalling the two main reasons of the stability of the quantized Winograd algorithm, so the enlargement factor and the large rounding error, we further enable the clipping factor to be trainable, thereby matching the range of values after the transform more optimally. This results in a smaller range that leads to a more suitable rounding and a better utilization of the quantized range. The last core component of this work is the introduction of complex numbers-based Winograd algorithm. This form of Winograd transformation improves the stability of the Winograd algorithm, as well as the utilization of the discrete range at the cost of a slightly less max savings. By also modeling the complex numbers-based Winograd, in addition to quantization awareness, we come to a formulation of training which fully captures all numerical instability sources under standard and complex Winograd algorithms, and it is able to compensate for them before deployment. To start with the experiment session, we compare Vici with Winograd post-training quantization and Winograd-aware quantized training by investigating the transformed weights histogram for a ResNet20 model. First, the post-training quantized Winograd is unaware of the quantization range at training time, leading to poor utilization of the available range and an asymmetric histogram. Second, the Winograd-aware quantized training improves upon the post-training approach by better utilizing the available range and resulting in a more symmetric histogram. However, there still remains a large range of numbers which causes large rounding errors. Third, in our Vici approach, further adding clipping factors results in a symmetric histogram, a full exploitation of the range and a narrow range which result in a smaller rounding errors, thus resolving the issue of the compared histograms. Moving on, we now compare our approach with baseline standard quantized convolution and standard quantized Winograd convolution on three datasets, namely CIFAR10, ImageNet, and Cityscape. First, we notice that the introduction of the trainable clipping factor drastically minimizes the degradation in accuracy compared to the standard quantized Winograd approach. It also achieves task performance comparable to the baseline standard quantized convolution approach, while having larger max saving between 2.4 to 3.4 times improvement. Second, by further adding complex Winograd, we can fully eliminate the effect of numerical instability and completely close the gap to baseline quantized convolution on all three datasets. This comes at a slightly lower max savings between 2.1 and 2.8 times. Finally, we compare Vici with state-of-the-art methods adopting quantized Winograd on two datasets, CIFAR10 and ImageNet. First, we highlight the number of scaling factors required by other works, which in many cases introduces more complexity to the hardware acceleration. Vici in comparison requires only one scaling factor. Next, Vici achieves better or equal accuracy compared to other works without adding any complexity to the algorithm on CIFAR10. Lastly, on the more challenging ImageNet dataset, Vici outperforms all other state-of-the-art techniques, offering better accuracy at the lowest complexity and largest max savings. In conclusion, this work combined four core components into a training formulation to mitigate and conquer the numerical instability problem of 8-bit quantized Winograd. We achieved high MAC reductions on image classification and semantic segmentation without degradation in task metrics, thus fully enabling the use of Winograd-based convolution on 8-bit general-purpose hardware without any compromises in prediction quality. These are our references. We thank you for listening, and we are looking forward to see you at WCB 2024.